Okay, hopefully others will join. Um, so we're going to talk about which routing protocols, and the two protocols we are going to compare side by side is ISIS and OSPF. Of course, you're going to talk about EIGRP in this forum. That would be the third one. Uh, there was a problem. The RIP had the problem. That's why we cannot, have RIP in the discussion either. And that's the reason we have the link set protocol, because RIP could not address those large-scale issues. That's why we have the link set protocol. So there was a similar talk that was given by Dave Katz in 2000 in NANOG 19 that happened in Albuquerque. And he basically talked about OSPF and ISIS. At that time, IPv6 really didn't kick in at that much. So what we are going to focus on after talking about OSPF and ISIS at the IPv4 or at the general level, we will concentrate on what are the changes that happen on the IPv6 side on these two protocols. So we will compare side by side what are the new things that have been added and how we are supporting IPv6 on these two protocols. So there will be two speakers. My name is Faraz Shamim. I'm a teenager at Cisco, been there for 13 years. The second speaker is also a teenager of Cisco, Khalid Raza. He's been with Cisco for almost 17 years or longer than that. So we came with the routing background, and we will put all the analysis that we have in the past, those teen years, what things that we have noticed, and basically compare the protocol in the light of that experience. So we'll go ahead and start that, comparing these two protocols. The first we are going to talk about at the basic level, the top-down view of these two protocols. So OSPF, when we talk about OSPF, is for the most part we say, okay, it has been optimized. We specifically concentrated on how to improve OSPF at the IPv4 level, just kept on concentrating towards the IPv4, try to make it simpler, which ended up making it more complex. So certain things that we have added in the OSPF that we talk about that have added the complexity, for example, the neighbor adjacency, which has to go through certain steps in order to be full. And when you form the neighbor adjacency in case of OSPF, you're not going to utilize the route until you go into the full state. So because of that, the reason because we wanted to avoid the transient routing issue. So for example, you have to forward the packet and you don't have the complete database, you don't have the complete picture, you may cause a black hole. So because of that problem, OSPF goes through this adjacency process, go all the way up to full state, and then says, okay, now I have all the information, now I'm going to install the routes in the routing table. And also, OSPF exchanges the granular database, so very small pieces of the database, especially the summary and external LSA, but when we talk about the router LSAs, depending upon the size of the network, in a large-scale network, you really cannot control the size of the OSPF network or the router LSA, so it has to be bigger. Now, going to the ISIS side, ISIS at the beginning, since the beginning, it was not designed for the IP, it was designed for the CLNS protocol, and that's what it used to carry. And then we made the changes in the ISIS through the extension that it can carry through the RFC 1195, that it can carry the IP side of that. So the way adjacency works in the ISIS, that as soon as the neighbor hears you, and this is it, you will be able to exchange information. You don't really have to wait through something similar that in OSPF we have to go through all the multiple states of adjacency. You don't have to go and wait at that level. So ISIS, when they can see each other, they will be able to use that route in the routing table. And for the concern that if there is a routing loop or a black hole concern, and there's a cool thing in the ISIS that there is a specific bit. Originally, it was designed for, if a router is out of the memory or something, you can turn on that specific bit, which is the overload bit. So you're not going to be use that router in the SPF calculation. You're going to do the calculation around that router. So that's basically we can use the OSPF ISIS overload bit if that is a concern. So both protocol have a way to minimize the loops. As far as encapsulation is concerned, OSPF it was written for the IP, so it is following the method that we are seeing with all the other protocols, that running directly on top of IP with the protocol number 89, just like any other protocol. And OSPF has the virtual links capability, so all the areas has to be attached to the area 0, the backbone area. And if that's not the case, then you have to go and configure the virtual link. Another thing that is with the OSPF, since it's running on the IP layer, so it is there's a possibility of the DOS attack, and because of that, the authentication scheme is highly recommended in OSPF. Now, if you compare the encapsulation side of the ISIS, it was originally designed as a layer 2 to work on the layer 2 carrying the CLNS packet. So it is difficult to do the spoofing in the ISIS because it works on the layer 2. And it sort of makes sense that layer 2 protocol carrying the layer 3 routing. So that's the way ISIS works. And there are some cases in the ISIS that there may be a partition of the area, but very rarely that virtual link, there is a virtual link in ISIS also, is very rarely implemented. Now we are going to talk about the terminology comparing OSPF and ISIS. So for those of you who are familiar with ISIS, you can compare the OSPF side by side from the terminology perspective. And vice versa, for those of you who are familiar with the OSPF more, you can see what are the equivalent terminology in the ISIS. So host in OSPF, so you can run OSPF with the host. For example, a Linux box, you can run OSPF. So that host terminology, the equivalent of host in ISIS is the N system or ESIS. So when you run ISIS, the routing between the host and the router, the process called ESIS, N system versus forming the routing relationship with the IS, which is intermediate system. Router is called IS, intermediate system. The links are called circuits in ISIS. Packets that we are familiar with the IPv4 is called protocol data unit in ISIS. We have designated router in OSPF. A similar concept that we have in the ISIS is called DIS, designated intermediate system. And we have a backup, we have BDR concept in OSPF, but there is no such concept in ISIS, and we will explain that in detail why you don't really need BDIS in ISIS. LSAs in OSPF are equivalent to LSP. Hello packet are called IIH, so intermediate to intermediate hello PDUs. We have DBD in OSPF. The equivalent of the DBD in ISIS is the complete sequence number packet PDU, or CSNP. The LS update is called LSP in the ISIS. Link state acknowledgement, so the acknowledgement portion is done with sending the partial sequence number PDU. Areas, we have the areas in ISIS also. It's called subdomain sometime. The non-backbone area in OSPF, in ISIS, the non-backbone are level 1. The backbone area in OSPF is equivalent to level 2 in ISIS. ABR, the term of ABR, the router which sits at the boundary of two different areas. So that ABR equivalent in ISIS, which is sitting at the boundary of level 1 and level 2, is called L1, L2 router. Virtual link, both protocol have that. In OSPF, when you do a redistribution, then we give a special name to that router which is doing a redistribution. We call it ASBR, Autonomous System Border Router. Now, in ISIS, there is no special name given to that router, but it will still have the same functionality that you're redistributing something in ISIS. Router ID is basically a 32-bit number in OSPF. which can be a loopback address or the interface address or manually written for the protocol. So that 32-bit number, the equivalent of the router ID, is called system ID, which is based on the MAC address in ISIS. Link state ID, which is a very specific OSPF term that are used in LSA details. There is no equivalent of that in the ISIS. Similarly, advertising router ID, there is no equivalent of that in the ISIS. So these are the terminologies. Now we will talk about these two protocols at the packet levels. Let's compare these two packets. So on the left side, we are seeing OSPF packets, and each line that you are seeing, that's basically a 32 bits long. So do we get any advantage of following this 32 bits? Maybe yes or no, but really it's not an advantage that OSPF is using a 32 bits chunk, and ISIS is just using 1 byte. If you see on the right side, ISIS common header is basically the 8 bytes. So starting from intra-domain routing protocol discriminator and go, and you can see all these things, which is the part of the common header. And right after that, you have the additional header field followed by the TLV, type length value. That is the protocol, that is the thing in the ISIS which makes it extensible, the TLV field. OSPF is basically a fixed header. And ISIS, you can see that is basically extensible header. So when they code it, they call it that, okay, we are coding it efficiently by giving it this 32-bit, but really it looks nicer on the document, but it's really not achieving anything by following this 32-bit format. The extensibility is the thing which really a very significant difference, because in OSPF, LSAs are extensible in a way that you can use opaque LSAs and extend the LSA through there. But if you look at the OSPF LSA itself, for example, router LSA, if you want to do anything specific in the router LSA, you cannot do that. It's a fixed size header. And look at the network LSA, it's a fixed size header. You cannot really do anything specifically in those LSA. So even though we are saying LSAs are extensible, but only we are talking in terms of opaque LSAs. Hellos were not extensible before, but with the arrival of the Cisco NSF, which is not Cisco anymore, it's a standard now. There are like 3 RFC that talks about that. And one of the RFC talks about the link local signaling, LLS signaling. So through the link local signaling, it basically extends the hello of OSPF, and you can send multiple things if you want, or you can basically extend the protocol and send exchange multiple things in the hello packet. So before that, this extensibility was not there in the OSPF, but with the LLS thing, it is now extensible. So what do we do with the LSA which is not recognized in OSPF? So for example, when we talk about OSPF type 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, that's it. If we go 12, 13, 14, it's not recognized. So what do we do if you receive the LSA which is type 14? In OSPF case, you'll just throw it away because you don't understand what is the what type of LSA is that. And that basically cause the issue if you want to do something specific and you just want the OSPF to propagate it from one end to the other, because what you are interested in is to send that get that information from edge to edge. The thing in the middle, you don't really care about what it does. So if you want to add something like that in the OSPF using some specific LSA, let's say type 14, OSPF is not going to carry that. You're just going to drop it in the middle. Now, you can probably leverage opaque LSA's idea and then, put that information inside of opaque LSAs and send it across. But by default, if OSPF sees anything which is not recognized, it's just going to throw it on the floor. In ISIS, since it's a TLV-based protocol, type length value, so it's an extendable protocol. You can do a lot of different things in the ISIS. You can add a lot of different things. That's why when the time came to add the IPv4 extension to ISIS, it was not really difficult to do, because all you have to do is come up with, a couple of TLVs one for the interface, the other one for the external and internal, and that's it. And protocol was extended through those TLV. If you have to add the IPv6 capability to ISIS, all you have to do is come up with the new TLVs in the ISIS and have it support IPv6 format, both from the interface level as well as the prefix level. So that makes ISIS very extendable. So you can do multiple things because it's a TLV-based protocol. And then there are certain situations there are nested TLVs. So the way it works that if ISIS has received some TLV which it does not understand, it's just going to skip it. It's going to go on to the next one and see if it understands it. So for ISIS, if something is not understood, that's not really a problem. But that was a problem in case of OSPF. Now comparing the type of packet we have in OSPF versus ISIS. So OSPF has the 5 packet: hello, DBD, link state request, link state update, and link state acknowledgement. ISIS has 3 basic types, and there are some granularity within those types. So we have the hello packet in the ISIS, but there can be 3 types of hello in the ISIS. It could be L1 hello, it could be L2 hello, or in a point-to-point case, it would be different types of hello. In the link state, the second packet is a link state packet, and it could be either from the L1 perspective or L2 perspective. So there can be 2 types of link state packet. Sequence number, there's a complete sequence number packet and partial sequence number packet. So these are basically the equivalent type if you compare it with the OSPF. The hello is a fixed format, but as we discussed earlier, with the help of LLS signaling, it's not really fixed anymore. We have kind of a hack that we can do the extensibility with the hello packet. And if it is default, especially on the broadcast media, it is sent every 10 seconds. And there is an intelligent sending on the NBMA because there is a pole interval, which is normally it could go all the way up to 2 minutes. On the NBMA. So there is an intelligent functionality built in with the hello packet in the OSPF. If you're running a special feature in the OSPF, it's called demand circuit to save toll charges. Back then it used to be very famous to save the toll charges of the ISDN. So you run it as a demand circuit. So then you suppress the hello over that demand circuit, and you will only bring up the neighbor if there is a change. But since you're already synchronized, you have all the information in the database. So we suppress the hello on the demand circuit. ISIS, again, extended through the TLV. The hello packets are extendable. And it is also sent every 10 seconds by default. And the DIS, which is if you're running ISIS in the broadcast environment, then the DIS is going to be 3 times quicker from sending the hello's perspective. So it's going to send 3 times faster than any other router on the network. So so basically close to 3 seconds is going to keep on sending the packet. These are the, so when we compare the LSAs versus LSPs, so in the OSPF case, we have, these are the LSAs that were defined. Some of them are really not being used. For example, external attributes. So it was defined quite some time ago, but I haven't seen any vendor using that. Group membership, I think one vendor implemented that. Cisco never implemented group membership. And if you read the RFC of OSPF version 3, the latest one, they have actually removed group membership from the documentation. And they say, okay, we are going to use that if there is a need for that. So for now, we are going to reclaim the bits which were used in the group membership. So the previous RFC 2740 has the group membership, but latest one, 5340, doesn't have group membership. And all the other ones are pretty, common one, the router, network, and some LSA. So on the ISIS side, we have, it can go from up to 256 LSP per node in the ISIS, and each LSP is considered with the different TLVs. So there are different TLVs that the protocol has been extended. the interesting one is 128, 129, which is directly dealing with the IP. So we have the internal IP routing info, we have a TLB for that. Since we are introducing another network layer, so we have a separate NLP ID for the IP, so you have TLB 128, which takes care of that. For the external, you have TLB 130 and 132 carry the IPv4 address. So all this IP that you were saying is IPv4. There are separate TLVs for the IPv6. When we extended the protocol for the IPv6, there are separate TLVs for that. And then we have a TLV for the wide metric. So in the metric, the default metric was not enough to do a lot of different things. So we have the extension on the wide scale metric. And that metric also, this TLV also have the capability to send internal as well as external prefixes in ISIS. Now, talking about the adjacency establishment, so the link state synchronization, so when you're exchanging the information in OSPF with each other, you have to make sure that you follow all the way up to the loading and then make sure that you have all the information before you declare that, okay, I'm at the full state. And this is happening because you want to avoid the loop situation or a black hole situation. On the point-to-point links, adjacency are established between the two routers, but on the broadcast link, we have a concept of DR and BDR in OSPF. We also have an MTU mismatch in OSPF, which was not there originally. So RFC 1583 does not have MTU mismatch capability. The MTU mismatch was added in RFC 2178 to the appendix G.9. So that appendix says, okay, that if you want to exchange the hello with each other and you go up to the DVD packet, make sure you advertise the interface MTU with each other. So if there is any discrepancy in the MTU, you're going to find it out right there. You don't have to go all the way at the end and find out, oh, there was an MTU mismatch. So, I mean, when I was, working in Cisco in TAG especially, we have dealt with so many cases of the MTU mismatch that, this was really a very good thing in OSPF that was added, that with the help of the MTU mismatch, you can detect it immediately. And especially with the new thing that they have added in Cisco, I'm not sure about the other vendor, that you can detect the MTU mismatch in both directions. So section G.9 of RFC 2178 says that, okay, if the neighbor has higher MTU than yours, then you're going to complain. But there's a specific feature that I'm talking about that it complains in both directions. If the neighbor has a lower MTU than yours, it still is going to complain. So that way, we completely capture this MTU mismatch issue. Comparing this thing with ISIS, so adjacency in ISIS is reported as soon as they see each other, or you can say equivalent to the two-way state. As long as you're two-way in ISIS, you will be able to see each other. You will be able to use that information from the routing perspective. Point-to-point works the same way that it works in the OSPF. And similarly, on the LAN segment, ISIS has a designated router, which is called DIS, and everybody basically send their information to DIS, and there is no backup designated router. The MTU mismatch this thing is there in the ISIS in the beginning, because what it does, it sends the packet and pads the MTU up to the maximum capability of the interface. So that way, you have the fully padded packet sending across both sides. So if in case you're running incompatible MTU on two sides and you're running ISIS, it will never, even the adjacency will never come up. So you know that, okay, some problem happening with the ISIS MTU, that's why it's not coming up. But when Dave was presenting in 2000, he was saying, this was probably a bad idea, or it was really not necessary to pad the MTU. But in certain cases, and again from the TAG background, we have seen a lot of cases where this have actually solved different types of problem that we have on a different. If two sides are sending a different MTUs. Okay, now to the database granularity. So when OSPF was designed, it was designed so we are going to send smaller chunks of packet. For example, you do some redistribution in OSPF, it's going to redistribute one LSA per prefixes. When you send the summary out from one area to another, it's going to send one LSA per prefix. So there is a lot of granularity that was added in the OSPF. But that thing cannot be kept if you have a very large scale network and you are running huge neighbors, for example. Then you have to put everything in one single LSA, the router LSA, and your router LSA size will be bigger. Similarly, if you have too many neighbors on the broadcast media, you're going to have a large network LSA because you have to report every adjacent neighbor through their router ID. So even though they wanted to make it more granular, but when we talk about in terms of router and network LSA, there's really no control if you have a large number of neighbors. And when OSPF sends out the update, it basically groups together in the LSA update and send it out for the flooding. And every hop there may be a requirement of removing some of the LSA or maybe adding some of the LSA. For example, you are at the border of a stub area, so then and if the flooding is coming from the back and it has an external LSA in it, at that point you cannot send the external LSA towards the stub area. So you have to remove those external LSA and send the link state update packet towards the stubby area. So small changes can yield small packets, but in case of router and network LSA, of course, you have to deal with the large LSA. Comparing this thing with ISIS, so ISIS basically it comes together all the different information in the LSP. So whoever is originating the packet, it can maybe send some links in it or send some external information or the stub link in that and send it all together as a part of the LSP. So it always flooded throughout with the same constant value of the MTU. Basically, it uses the same value, so the LSP MTU is an architectural constant which remains the same throughout the network. You don't really change that on hop by hop like in OSPF. So in that case, if there is a small change happening in the ISIS, a small change that can that you have to calculate the entire LSP, but the size of the packet doesn't matter. It's how frequent you are doing it. That's the main thing. That's an issue. And there are some ways that you can correct this thing through the implementation. But these are the issue with the ISIS. It also helps the convergence from the flooding point of view. So it will converge faster in ISIS. Okay, the DR concept, designated router. So both protocol elects the DR, and the reason for the DR is because you are trying to address the big O of n square problem. You have a graph, connected graph, and the number of edges that you have in the graph, that's the number of adjacency you're going to have. So as soon as the number of neighbors grow, you're going to have n square problem when you deal with the flooding. So we have the concept of DR and DIS in ISIS that takes care of this flooding. So OSPF elects both DR and it also have a backup designated router. The reason we have a backup in the OSPF because OSPF goes through this complex adjacency process that is going to start from two-way and then go start, exchange, loading, and then full. So this thing takes time. So what it does is it has a backup designated router which does the same thing. So you are fully adjacent with DR as well as BDR. So in case DR goes down, you don't have to reestablish the adjacency with the BDR. You're already full with the BDR. All it has to do is assume the role of the DR and takes care of the flooding. So that's why BDR concept is really needed in the OSPF. And DR ship is sticky. So that means if you are a DR in the OSPF network, it's going to take about 2 or 3 steps to change the DR. because you cannot just plug in a router with the highest priority and then say, okay, that router becomes a DR. In OSPF case, they took care of that because they're saying, okay, that's going to add the instability to the network. If a router comes in with the highest router ID or with the highest priority, we don't want the network re-election. We don't want it to be re-elected. Let the DR stay where it is. And if you have to introduce a DR, it's a complex process. So what you do is you have to bring down the current DR. Then what will happen that the BDR will take over the responsibility of the DR. So BDR becomes a DR. That new router that you want it to be the DR, it has to wait because when you do this thing, the new router becomes a BDR. And then you have to do this thing again so that current DR will die and this BDR will take over. So basically, at least there's a two-step process when you want to introduce DR inside the OSPF network. Now, if you compare this thing with the ISIS, there is no backup designated router concept in the ISIS because it's not going through this complex adjacency between the two nodes. So it doesn't go through the two-way XSTAR exchange, and send this granularity of the database with each other. It's basically send just a couple of CSNP packet and you have the topology information. So synchronization in the ISIS is pretty fast. So that's why when you lose a DIS in ISIS, very quickly you're going to be electing a new DIS and you're not going to be seeing any issue with that. The DR ship in the ISIS is deterministic, so that means whoever has the highest priority or the highest MAC address is always going to take precedence. But that can be a problem because in the real network, if you introduce a router which has the highest priority, it's going to take the DR role and it can cause disruption in the network. So there's a way, we did this thing in the NLSP. For those of you who remember this NLSP protocol for the for the IPX. So as soon as you become a DR, you bump up your priority by 20. So that that makes you the DR. So if somebody comes up with the high priority, your priority should be the highest. So you're not going to lose this DR ship to the others. The DR election, so every LAN interface, it has to go through this waiting state because it has to know that if there is a current DR present on the network, I don't want to participate in the election. So, so the new router will not try to preempt. So, like I said in the previous slide, so the re-election happen only when the current DR or BDR goes down, and that's again added for the stability, which is in the ISIS case, since it happens so quickly, we don't really need. We don't really see a problem in the ISIS. So a new router attached to the segment, can cause a switchover. But if we implement that hack, that when as soon as you become the DR, bump up the priority, so that can be eliminated in the ISIS. So any advantage that you see in one protocol that is not in the other protocol can easily be added, and it has been going on throughout the year. So something that we saw very cool in the ISIS, OSPF took it. OSPF has some cool thing in the in there, and then ISIS took it, or vice versa. So at this stage, both protocol are pretty much the same. So we really cannot say that okay, this protocol is better than the other. I'm not sure what was the intention of you guys that okay, after attending this session, you can say okay, one protocol, this one is better. So you're just going to compare it and present it to you. Now it's up to you to decide which one makes more sense for your network. Now, on the LAN flooding, there's another thing in the LAN flooding side that OSPF uses the concept of send the multicast packet and do the acknowledgement via unicast. So that takes care of only 50% of the flooding, which is still not, that good of a reduction. So because everybody is fully adjacent with the DR, so if something happens that needs to be retransmitted, it's going to happen on per neighbor basis. So that means if you have 50 neighbors and if you go up to 100 neighbors, you go to 150 neighbors, this problem is going to get worse and worse because you have to maintain this adjacency and anything that has to be retransmitted, you're going to do this call and response, one device, because you are sending this unicast retransmission. So that becomes worse as the number of neighbors grow. So, but in ISIS case, it sends all the information through the CSNP. So you're not really forming this stateful relationship. So in ISIS case, if you have a 50 neighbor or 100 neighbor, you're still going to follow the same thing, send this multicast LSP on the wire, and everybody will be listening to that. If some information is missing, they're going to send PSNP, the DR will send the CSNP, and you will be synchronized. So you're not really maintaining this, very at the granular level with each neighbor. So that's something which has in the ISIS. So this flooding is basically constant depending upon the number, regardless of the number of neighbors that you have in the ISIS. So whether it's 50 or 100, it really doesn't matter in the ISIS. Now, in terms of areas in both protocols, so OSPF can sit in many areas. And if the backbone is attached, it is an ABR. And if there is no backbone connectivity, then you may be called an ABR per RFC 2328, but you will not originate summary LSA. So the definition of ABR is tricky. So RFC 2328 says if you're connected with two areas, doesn't matter if one is area 0 or not, you will still be an ABR, but you will not originate summary LSA. But if you are connected with area 0, only then you will originate the summary LSA. There is an RFC which capture what has about the Cisco implementation, RFC 3509, which capture all this thing that what are the conditions we originate the summary LSA and the definition of the ABR. So there is a specific bit in the router LSA called B bit. If it's on, then router is called an ABR. If it's not on, then the router is not called an ABR. The thing is, in Cisco implementation, we do not turn on that bit if area 0 connectivity is not there. So that means, this router, the ABR, is not going to originate the summary LSA. In case of ISIS, each router belongs to one area, and multi-area, there is a thing called multi-area in ISIS, but it was not intended for the IP version of the ISIS. It was intended basically for the CLNS protocol, and it was also intended to do the migration. And it was never intended to have, normally you can have two areas. So still ISIS has level 1 and level 2, and within each level you cannot have multi-area. That's, if it works, then it's not doing the right thing. It's not supposed to work. There are some customers, who have tried this thing, but it's not supposed to work with the multi-area. Okay, links and area. So in OSPF, link can only be in one area, and router must agree to that specific area. So if you're in area 1, the other side is area 2, you will not be able to form adjacency with each other. Area border crosses the router in OSPF. In same situation, if you are in the ISIS case, if you have two different areas, they will form adjacency, but there will be an L2 adjacency. So if the area doesn't match, in ISIS case, you're going to form L2 adjacency. Otherwise, normally ISIS can be associated with L1 area, L2 area, or you can have that same link you can have in both L1 as well as L2 area. So that is basically a difference in the ISIS. The area types, so OSPF has a regular area, it has the stubby area, it has totally stubby area, it has NSSA area. So all this thing with or without summary. And if you compare with ISIS, so ISIS, the closest definition that you can get from the ISIS is totally stubby NSSA area, if you want to compare the ISIS, because you can leak the information in the ISIS. You have to do a specific feature in the ISIS, which is the route leaking feature. Normally, L2 information should not be leaked into L1. So that basically brings up a point that, okay, how the L1 router determine which path is more optimal. So that is a problem, because if you don't leak that specific route, then it can go to any of the L1, L2 router, and it may pick up the one which is not optimal. So to have the optimal routing in ISIS, you can just leak the route in ISIS. So this is one of the examples that we can say that in OSPF case, we used to leak the inter-area route in the area, and ISIS was behaving differently. So ISIS took this thing and then implemented through the route leaking. So with the route leaking, then you can behave this in a more optimal fashion. The inter-area routing, so OSPF has optimal inter-area routing support, so end-to-end metric is calculated. So we can provide the injection of inter-area route in any area by the use of no summary, which makes an area as a totally stubby area. So normally we take the information from one area, send it to the other area. That's the normal behavior. But if you want, we can say, okay, do not send anything to that area, but only send the default. So that's the behavior of when you use the no summary option. Cisco has a specific way to control every single thing that you want to send. So maybe when you send the summary LSA, you can control which summary LSA you need to send to that specific area. Because the summary LSA is very close to the distance vector behavior in OSPF. So you take that information and you're propagating it to an area. You can say, okay, I want to control only 3 or 4 LSA I want to send in that area, and I want to prevent the rest of them getting into the area. But the default behavior, either you send everything, or you summarize it and send everything, or you don't send anything with the no summary option. But there was no such thing, something in the middle. So this feature actually provides something that gives the control to the user. Whatever you want to leak or prevent, you can do it through this. Okay, intra-area routes are announced to the type 3 summary LSA, and you can summarize if you want at the ABR. And if the backbone connection is active, then ABR consider only the backbone summaries and re-announce them to the non-backbone area. So normally, an ABR can take the information from any area, and it has to be an intra-area route, so a local route for that area, and then it can generate the summary into a different area. But in case of a backbone, there is a possibility that behind that backbone, there is another area connected to the backbone, and when this ABR receives that area route, is going to be inter-area route. So then you will be able to create the summary LSA and send it to this area. So that is an exception that in case of the area 0, you can generate the summary LSA if the route is inter-area in area 0. But you have to be connected to area 0. If you're receiving that inter-area route from another area, this thing is not going to happen. So this exception is only in case of a backbone area. So take that route and then generate the summary LSA into the different area. So ISIs did not have this inter-area routing. So if you want to leak something in ISIS, you have to do this route leaking capability in the ISIS. And also, if you want to leak an external, that's not a problem with the ISIS. You can just do the redistribution. Even though we are calling it, totally stubby, but it's close to NSSA, where the stubby nature of the area is preserved, but you are still able to leak external routing information. That's why we are comparing it with the NSSA of OSPF, that you're limited leaking the routes in ISIS. External routing, so when you do the redistribution in the OSPF, you generate type 5 LSA, and it's going to be 1 LSA per prefix. So that makes it more granular. So the idea is if something is flapping constantly, and then you can just, basically it's not going to be that impactful because it's just 1 LSA which is flapping, and you can control that. In case of a multi-area, OSPF requires ABR to generate type 4 LSA, which is in addition to type 5. But if it's one single area environment, then you don't really need type 4. Type 4 is only needed when you have multi-area situation. And only 1 copy of the LSA per domain are flooded throughout, and the externals will not be flooded into stub area or the NSSA, because NSSA is also an extension to the stub area. The administrative tag can be set in the OSPF, so you can do the tagging while you're doing the redistribution, and maybe you can do something else based on the tagging, so OSPF lets you do that. And external routes will be represented in completely in a different way than you represent the internal routes in OSPF. So you can look in the routing table, you can clearly see that, okay, which one is external and which one is internal. And if you want to do the summarization of the external, you can either do it, you can only do it on the ASBR, which means only the router which is doing the redistribution can do the summarization. But if you're running the NSSA case, NSSA will let you summarize one more time before it translates from type 7 to type 5, because the ABR is regenerating those type 7 LSA into type 5. So at that time of regeneration, you can control what you want to regenerate. In ISIS case, there are two TLVs which used to carry the external information, TLV type 130 and 135. And every L1, L2 router re-announce the external information to the L2, and if the route leaking is configured, it's going to announce the external to L1. And there is no administrative tag in the ISIS, so you cannot really tag the external in the ISIS. An external route cannot be differentiated, so if you're looking at the routing table, you cannot really tell whether it's an external route or internal route. It's just going to look at, the only differentiate part is either it's going to look like L1 or L2, but you can't tell if it's an external or not. And you can do the summarization, just like OSPF, you can do the summarization at the L1 and L2 router. The summarization in case of OSPF can only be done on the ASBR, and ABR in case of the NSSA. But in the ISIS case, you can summarize at the L1, L2. Number of neighbors. So both protocol can have significantly large number of neighbors. Whether it's a good thing or not, you know, from the design perspective is another thing. But can the protocol support that? Yes, the protocol will support it. And ISIS, since has been deployed in a very large ISP network, so there are large number of neighbors because they didn't want to create multi-area situation. They just wanted to deal with one single area. So we are going to see that there are large number of neighbors we find in ISIS more than compared to OSPF. Now the scalability issues, we are going to talk about that. What are the limits? In OSPF case, so the limits is basically on the network and the router LSA, because you have certain limitation or boundary that you can go up to the maximum this size, or approximately 5,000 links you can represent in one single LSA, because more than that, then you have to deal with the fragmentation. So that's so that is basically a limitation, but any sane network will not have 5,000 links, 5,000 neighbors in one single router. So that's basically, even though this is a limitation, but I wouldn't really call it a limitation because it's not a right thing to do anyway. The externals and inter-area routes are unbounded, so you are going to keep on creating the externals or inter-area until you run out of the link state ID or the sequence number. So you keep on generating that. ISIS topology are limited by 256 fragment per IS for all route types. And again, it is basically a very large number, and there are some hacks that you can increase that number. But again, it comes out to the point that, if you want to design your network properly, then you really shouldn't be running into these scalability issues. The database churn, so both protocol have a time limited database entries, so that requires refresh after a certain period of time. ISIS basically start at the highest level and then count backwards, and it has 16 bits for the aging, and that gives about 18.7 hours of lifetime, which is pretty huge. OSPF starts in the opposite direction, so it starts at 0 and then go up, and then every 1800 seconds, about 30 minutes, it refreshes the LSA. If the LSA is not refreshed for 1 hour, 3600, it's just going to remove it from the database. And then there is a do not age thing in the OSPF, which basically keeps the LSA forever until something changes in the topology. But the problem with the do not age LSA is if one router in that area is not capable to understand the DN bit, which is the do not age bit of the LSA age, it's not going to let you originate the do not age LSA. So if you're originating zillions of routes in your IGP, it's not really a good thing to do because the protocol will not scale that way. I mean, IGPs are not designed to carry thousands and thousands of routes. IGP, the primary purpose of that should be to take, from one place to the other and just rely on the next hop, and it shouldn't be carrying, unnecessary information in the routing table or the database, because if the size of the IGP grows, that makes a protocol unstable, whether it's ISIS or OSPF. Now, one problem which is with both ISIS as well as OSPF is the flooding problem. And this is the full mesh issue. When you have full mesh connectivity, then it uses the formula of n into n minus 1 divided by 2, basically the connected graph edge formula. If you want to have a connected graph, the number of edges would be n into n minus 1 divided by 2. So that means if you go up to, as soon as you grow the number of routers, the fully mesh router, this number, the n factor becomes significantly large. So for example, 50 routers, if you connect them in a fully mesh situation and you use the formula of n into n minus 1 divided by 2, then that means the total number of adjacency that you have to maintain on the 50 router is about 1,150 or something, 1,150 adjacency that you have to maintain. It's not just a problem of maintaining the adjacency. What if you have to flood some information, a new information that a router has to flood? It's going to send that information out to everybody because it's fully meshed. And then everybody else is going to flood the information back to everybody else. So that can go up to the n square problem because you have to flood it on every single link. And if you are dealing with a very large router LSA, then it can even go to n cube, which is really, really bad. And that's just a link problem. Suppose you reload a router in a fully meshed network. So reloading a router is even worse than having a link down or up. Because reloading a router, every router is connected to that particular router which went down. Every router is going to regenerate the router LSA and send it to everybody else. So you add n on top of whatever is happening already. So again, in case of the worst situation where you have a very large router LSA, then it can go to n4, n to the power 4. But n cube is the normally which we are going to see. And I wish, there was a way we can show it, because for that you have to have 50 routers, fully mesh, connectivity. And because there was a customer that Khalid and I was working with, he wanted to run 50 routers in fully mesh network. And both of us were completely against that. We said, you're going to run into this problem. So theoretically, we can tell you that, okay, this is a problem. But if somebody can connect 50 routers together and then show it that, okay, this is a problem that you will run into, then we will have some data to work with. There is a way to avoid this fully meshed situation, is don't do it. That's the easiest thing to do. Or if you really have to do it, then you have to do this lot of administration of controlling which router is going to send what information, and this is a lot of manual work. So essentially you are creating a DR kind of behavior in a fully meshed situation where you are sending, okay, if I receive that information, only that particular router is going to send this information to everybody else, and nobody else should be sending the information back. So the way you can do in ISIS is through the mesh group, and the same thing you can do in OSPF with the database filter out command. So again, this command is there, but it's a lot of administrative overhead to go through this painful process of, defining what information goes out where. So fully mesh, both in case of ISIS and OSPF, is really not recommended because you will run into a lot of flooding issues, and which eventually will melt down the network. So that's my portion of the presentation, and I'm going to pass it on to Khalid, who is going to talk about the IPv6 aspect of these two protocols and some convergence. Okay.
So good afternoon. This is a question that has been there from 90s and 2000, which routing protocol? The reason we're bringing this up again is, again, people have started to ask this question. I've done OSPF v2 in my network. I'm looking into IPv6, dual stack. Should I do OSPF v3 or ISIS? I've had this discussion with customers recently, which protocol to choose. Fortunately or unfortunately, we all have our biases, right? If you ask Faraz, he'll always say OSPF v3. Not that I'm going to advocate ISIS. You ask me, I'll always say ISIS, right? But the point we have in this presentation is it boils down to operational experience. Even when you're going IPv6, look at what you're operationally familiar with. And that's the protocol you choose. So the comparison that we saw in this presentation Faraz did was mostly between ISIS and OSPF version 2. There were some interesting problems that people always brought out against OSPF v2. He said it ran over on top of IP, so it was hackable. One of the problems it had was the summary and external LSAs. The information that was carried by those two LSAs were in the basic header. So you had to generate each external or summary individually. You did not do fragmentation of the packet. So anytime you had a neighbor adjacency issue in case of OSPF v2, you also had to see the capability of the device where you were implementing, that how much buffer space you have to have for that large router LSA before the LSA got created and then it was given to IP to do fragmentation, because OSPF didn't do fragmentation. So OSPF v3 addressed a lot of those issues. Protocol processing per link, not per subnet. Your adjacency was dependent on the subnet you were sitting on. So all sides will have to have a common subnet. The subnet IP prefix related information was part of your SPF topology. So any subnet changes I made, I had to force a full SPF. Now, in case of OSPF v3, since IPv6 brings the concept from subnet into link, you connect to a link. You have your link local neighbor relationship. That link local address space is utilized to form adjacencies. Now you can have routable prefixes that will ride on that link, which connects you to the outside world. So those routable prefixes are not part of your topology anymore. That's a separate link state that's introduced for those routable prefixes that connect those subnets. And those prefixes that connect those devices don't have to be identical, because they're not responsible for your adjacency formation. The other thing is additional flooding scope. We had a flooding scope that was area-wide or an autonomous system-wide. One of the things people always brought out against OSPF version 2, as Faraz had mentioned, is the extendability. If I didn't understand the LSA, I will drop it. Now, in case of OSPF v3, that problem is solved. You've defined the flooding scope. On top of it, you say, if it's an unrecognized LSA type, I will tell you what to do with it. Either keep it local on the link or store and forward it. You don't do anything with it, but there are pieces in the network that they do understand this new LSA that I'm trying to flood. So use that to flood it to others, although you're not utilizing it. So that was another thing that was advantageous for ISIS, which OSPF v3 brought into it. So use of IPv6 link local addresses. Another interesting thing was OSPF, if you ran OSPF multiple instances were not part of the protocol itself. If you use, I'll say Cisco device, if you set up a Cisco router and you say OSPF process 1 and OSPF process 2, you redistributed those processes and they exchanged information between each other, but they were not part of the protocol. So I could not enable OSPF instance 1 on a link and want to completely protect my OSPF instance 2 with that information that is in instance 1. I want that separation. Say at a later stage, I want to use different address families and I want to separate them. So I didn't have that capability to do it because instance was not part of the protocol. Now instance ID is part of the protocol. Because you do not just flooding separation, you do SPF separation, complete resource separation between the two instances. As I said earlier, handling of unknown LSA types. Packet format LSA header changes. And as I said earlier is, you have taken out the prefix related information that you had forced in the router and network LSA in OSPF version 2. Now OSPF basic LSA headers are more inclined towards topology information, what ISIS had. You don't have all the prefix information that you were forcing onto the protocol. So, as I said earlier, IPv6, in the case of OSPF, and we know in IPv6, you use the term link instead of a subnet. All the interfaces connect to a link. Multiple subnets, as I said earlier, you can assign multiple subnets because the link local is used to form adjacency. So that's intra-area prefix LSA will be used to advertise those links that are routable links. Not all routers on the common subnet have to share those routable links for IPv6 case. So also you have made changes for OSPF protocol packets and the content of hello packets and network LSA. As I said earlier, you're taking out topology, prefix related information. You're just reporting topology information in router network LSA. If anybody of one is interested in a complete presentation about OSPF, 60 to 80 slide presentation we have, which goes through each and every LSAs and explain what functions and how it has changed as compared to OSPF v2, please send me an email. I'll give you my email address end of this presentation. I'll be happy to send it to you. Your basic packet types that we saw in OSPF version 2, they're all present as it is. You have hello DBD packet, link state request packet, link state update packet, and link state acknowledgement packet. All exist in OSPF v3. Mechanism of neighbor discovery and adjacency formations are still quite similar. Your interface types are still similar. You have point-to-point, point-to-multipoint, broadcast, NBMA, and virtual links. LSA flooding and aging are identical. And your LSA types are nearly identical. Not all of them are identical. Some are renamed and some are new. There's a new LSAs two new LSAs have been introduced. So as I earlier said, if you look at the two packets between for OSPF and ISIS, OSPF v3, you have functional codes that are introduced now. You have a flooding scope, which is the U-bit, and the S1, S2 bit indicate what's the flooding scope. Remember in OSPF version 2, we had two flooding scopes. We had AS-wide scope, the externals were flooded throughout the autonomous system. You have an area-wide scope. In case of OSPF v3, we have a link local scope. So LSA is flooded only on the local link. So if you've done some introduction of something new, you can flood this only to the link and upgrade only the routers that are on that link. Now U-bit is what is called whether you recognize this LSA or you don't recognize the LSA. And if you do, what do you do with this? And I'll show you in a second how do you handle an unrecognized LSA. Because what was a major complaint against OSPF as compared to ISIS, that even if you don't understand, you should be able to flood it. So it gives you upgradability, because the two places that you want protocols to be extensible is the hello mechanism in the initial stage and what you call NLRI, network layer reachability information. Either you're doing it through whatever LSA method or you're doing it through LSP methods in ISIS, your NLRI should be upgradable without major changes to the network. So when you get your U-bit, in case of in v3, you say treat this LSA as if it has link local scope. if your U bit is set to 0. So the change I've made, the upgrade I made, it's local to you. If this bit is 1, it says store and flood this LSA as if type understood. Although you have not been upgraded, so if I introduce an LSA type 53, right, a router that does not understand it, if sees the U bit set to 1, says I'll store it and I'll flood it. So that there are routers in this network who do understand this LSA. Now, if you looked at router LSA, you had 1, 2, network was 2, summary was 3, 4 was summary SBR, 5 was external. So now you have these S2, S1 bits, which actually indicate the flooding scope. So router LSA is now 4001. Says this is the flooding scope, because if the flooding scope is 10, that's 4. And if your flooding scope is link local only, you say 00. Right? If your flooding scope is area flooding only, you say 01. If your flooding scope is AS-wide only, which is external, it's 10. So along with the LSA type number, you have a flooding scope attached to it. There is no difference, then router LSA still is one functional code with a flooding scope. So essentially, I think what I'm missing is I am missing a slide which talks about all the LSAs. So you have your router link state, you have your network link state, you have a summary link state in OSPF v2, which is now called as inter-area prefix LSA. It's renamed, behavior-wise it's similar. With one difference, that the LSA header in case of summary link state in OSPF had the information about the LSA. That's why you had to make all of them as individually. In case of OSPF v3, that information is removed from the header. Now you can pack large number of summary LSAs into a single packet in OSPF v2. Same thing with external. That is an efficiency that has been introduced in OSPF v3. Then you have intra-area prefix LSA. Well, if you look at OSPF version 3, what they have done is they've separated, as I said earlier, the topology from the prefixes. Prefixes come and sit on top of links. In OSPF v2, the subnet was part of your topology. In OSPF v3, subnet or the network you're sitting it on is not part of your topology. So the way you map that is you build your topology of the nodes and the links that connect, and which node, on top of those nodes and links, your intra-area prefix LSA attachment is shown. So all the prefixes that attach to those interfaces are flooded now through intra-area prefix LSA. It's kind of the way ISIS did it. You had your neighbor relationship on your topology information that you're building with the IS neighbor, but you were adding your prefixes through IP reachability and LRI. So it's a similar concept that OSPF has adopted. Also, you have your link LSA, link local LSA. So your link local LSA is essentially tells you the next hop that you're going to utilize, or if you're sending subnet information which the other neighbor doesn't have. So which is actually your next hop to reach that destination. And as I said earlier, I'll give you my email address. We have a pretty long presentation that covers each LSA in depth. So this, within 1.5 hours comparing the two protocols and putting some IPv6 was not justification to either of the protocols. So ISX extension, one of the simplest thing with ISIS has been add a new TLV. Those of you who've been in the industry for a long time, if you remember Hank Smith, who did most of the ISIS early work for Cisco, Hank would always tell you when we used to work on OSPF, he says, oh, it's easy for me. I'll go add a TLV. So that was a standing joke. If Hank could do anything, he'll just add a TLV. So with ISIS, that was the simplest thing. All I had to do is to add the TLV, the NLP ID support. I can define the new NLP ID for IPv6. I can define a new TLV for IPv6 reachability information. I had it for IPv4 reachability information. Exact same concept. So if you're an ISIS guy, you say, oh, you've just added a new TLV for me. And now with TLV formats, of course you have your sub TLV. So, but the TLV number that you use for IPv6 reachability is TLV 236. IPv6 address, which you use IPv6 address TLV, it's also modified to carry IPv6 address. Again, it depends on what package it's inside. If it's inside an IP, if it's inside a hello packet, then of course you use the link local address. If it's inside of LSP, you use the IPv6 assigned subnet address. So how do you actually deploy ISIS in case of IPv6? You have multiple ways that you can look at in deploying ISIS. You can run a single topology, IPv6, IPv4, ISIS, single topology, single SPF. What's the requirement for that? All interfaces configured ISIS v6 must support v6. Cannot be configured today with MPLS-TE because we have not defined TE IPv6 extensions for traffic engineering. All interfaces considered with ISIS for both protocols must support both of them. You're trying to do single topology, single SPF. Again, since ISIS rides on top of it, you can do an IP and IP encapsulation. The only way to transport ISIS against tunnel hop is IPv6, is GRE. What is more looked at by people today who are not trying to build identical congruent topology between IPv6 and IPv4 is multi-topology ISIS. OSPF v2 and OSPF v3 runs ships in the night. There is extensions that are going on for multi-address family support for OSPF v3 to carry IPv4 prefixes as well. But if you look at today, your OSPF v2 and OSPF v3 will run ships in the night. For multi-topology, this is the mechanism that allows you within a single domain to run multiple topologies, one for IPv4, one for IPv6. So again, simple TLV addition. You do IPv6, IPv4, and you can do multicast topology, separate topologies, and then the possibilities are limitless. You can build QBR-based topologies. So you build independent topology per protocol. So current ISIS specs and all implementations forces all protocols carried by ISIS to agree on a common shortest path tree. We're changing that with multi-topology. You used to require single SPF with multi-topology, and if you require a single SPF, you were forced to have a congruent topology. Now, so all the links, as I said earlier, needed to understand identical topologies. With multi-topology, the beauty of this is not every link has to have the congruent topology. So you can selectively introduce V6 and part of the network where it doesn't have to follow the identical already running existing OSPF IPv4 topologies. So each router knows which topology it will establish an adjacency with, and that's done through configuration. During your adjacency establishment, peers need to agree on the topologies. So you exchange the topology identifiers through IIH, intermediate system to intermediate system hello. That I want to establish this topology, you send it on IIH, and you will agree on the topology that you're trying to build. Now there is interesting discussion between the two concepts of the ships in the night, I said between in OSPF v3, and multi-topology with ISIS. ISIS does give you the separation of SPF with multi-topology, but it's still a common flooding domain. The flooding information will reach everybody, and you will see that information that even if you're not part of that topology, your SPF is not executed, but you will receive the information because you're still part of the same flooding domain. So essentially, your databases can become large. There is another approach that's been looked at is called multi-instance. Again, then at that point, you will run ships in the night. Each instance of the protocol on a given lake, they're independent of each other. No SPF sharing, no flooding sharing. Any topology information changes happen in instance 1 has nothing to do with instance 2. So this literally enhances your ability to isolate resources and let you prioritize. If you want to do convergence, in what pieces, how do you want to affect that, how do you flood this, each and every resource would be separated based on the instance. You can do instance prioritization for PDU, for your PDUs for routing calculations. So today, if you do fast convergence, if you're running ISIS, you have fast floods in that. And the first fast flood in ISIS's case in Cisco says the first 5 LSPs are flooded before you even look into executing SPF. And one of the interesting differences between, Faraz mentioned, between OSPF and ISIS is this flooding is ISIS does not regenerate an update and flood it at every hop. Whatever is received, I will flood it unaltered. That's why your MTU has to be consistent. In case of OSPF, I don't know when I'm flooding what information needs to go to this neighbor because this neighbor might not be requiring this information. As he said, I might be flooding this information into a stub area, so I have to take this information out. So if you're trying to do fast convergence with ISIS and you have multiple topologies, this instance will give you the capability to separate that which PDUs are prioritized to get fast flooded, which I can stagger. Your OSPF is currently based on multi-instance. Adding multi-topology is very easy for OSPF v3. It has not been added, but there's drafts, I think there are current drafts to add address family v4 to as well to OSPF v3. And it's a matter of time that you can add a multi-topology. Multiple address family support, as I said earlier, is already there. In case of ISIS, multi-topology support has been there for a very long time. People who have deployed ISIS and are looking into, who want complete congruent topology in their core saying, I'll look at multi-topology, and it has been there, it's stable, I know this. Multi-instance DAP is out there now. So which one is better? I started my career in operations. I love looking at smaller databases. If I'm troubleshooting IPv4, IPv6, I always look at every network from troubleshooting point of view. So I'll always prefer a smaller multi-instance. But from development, if you talk to some of the development guys in Cisco, they'll always say, hey, multi-topology is better, easier. So it's a perspective. If the operation guys pushes, then you will see more multi-instance. If the engineering and development guys have their way, they'll always say multi-topology. Some minor things around convergence. If you, that's the other part of our job. We spend a lot of time looking at convergence for both OSPF, ISIS, IGPs. Convergence is simply a few-step process. A, failure detection, which is not, I would strongly discourage to use routing protocols to do link failure detection. There are other better schemes there. Change in propagation. So if I create my new LSA or LSP, how quickly I flood this, what are my methods for flooding it to all the neighbors, how efficiently I need to do this, how the tuning should be done based on link failure, node failure, using exponential algorithms that are out there available. Initial wait for SPF computation. Should I wait for SPF computation, taking a node failure into account and set my first value to that, or should I take my SPF computation initial wait to be mostly link failure based, because most of the failures in the network are link failure based. And then with exponential algorithm work that has been done by the vendors, is, should I take the step size according to take care of the node failure and the initial weight to take care of a link failure? Or should I keep my initial weight to be based on node failure and then it covers link failure anyway? So those are interesting things. You'll have people with varying opinions. Of course, we have ours, but it depends on how quickly you want the convergence to take effect in your network. And of course, time to run SPF, dependent on topology, dependent on the information flow inside of the network. Reducing the size of LSAs or LSPs is also efficient method to have your convergence and SPF calculations improved. So, convergence consideration, the IGP will compete over processor cycle based on their relative tuning. So howsoever you have tuned one protocol or the other. If you've tuned IPv6 and IPv4 IGPs the same way, so of course, naturally expect doubling of the standalone operation for your convergence time. A lot of people prefer, in case, to start initially with IPv6 to have a little slower convergence because IPv4 is still carrying my large customer traffic, and that's where most of my revenue is coming from. So I'd rather have those timers tuned to a very quick, efficient, lower values, and then I'll gradually, with experience, tune IPv6 and see how well the implementations have been taken care of. So whatever work has been done from fast convergence point of view, for OSPF v3, you do have carrier delays. That's a detection method. Hello dead timers, they're there. I don't advocate fast hellos. I don't like fast hellos. I think the routing protocol's job is to not detect link failures. Its job is to remain and maintain adjacency. BFD is available. You have LSA packet pacing. Again, it's an in-depth discussion of how each one of these parameters from flooding convergence point of view could be looked at. You have your interface event dampening. You have your LSA throttle timers for both LSAs and SPF, your exponential throttle timers. You can tune your maximum link state arrival interval. Again, these are all throttling mechanism to back off your neighbor based on too much LSA being flooded. So in case of OSPF, you do have an arrival interval that is minimum required for the before you start accepting LSAs. ISIS does not have any similar mechanism. I think it's John Postel who said something that be very careful what you send and be very liberal what you accept. So ISIS is on that methodology that, okay, I'll be very careful what information I send out for my throttling. So there is no arrival control in case of ISIS. OSPF says, okay, if somebody's really bugging the hell out of me, I can still tune my, let's say, arrival timer to take care of what frequency I will accept these LSAs. All the other functionalities like stub router, Cisco NSF is still not available for OSPF v3. You do have a graceful restart available for OSPF v3 if you're thinking about implementing it. For ISIS, almost everything is available. You have your fast hellos, BFD, LSP pacing, interface dampening, exponential throttling timer for both. Because remember this, today we have mostly multi-topology ISIS. So it's not a big change. I can do pretty much what I've done for v4. I can done for v6 as well. Your PRC, incremental SPF. For your resiliency, you do have both Cisco NSF and graceful restart available if you decide to implement for these protocols. So, conclusion, OSPF is more well documented because it's deployed in more enterprise accounts. It's much more available. You can find white papers. You can find books of varying quality in OSPF. ISIS is understood within a niche, SP market. Now enterprises are actually sort of being forced to start understanding ISIS. If anybody is following Trill, layer 2 multipathing for data center environment, it's entirely based on ISIS. So if you're an ISIS guy, understanding Trill is not that much difficult for you. So within data center environment, because of the spanning tree issues, ISIS is now being seriously being considered. If the large enterprise I'm talking to, they are seriously looking into ISIS for layer 2 multipathing reasons. And largest networks are built on ISIS. So again, I would always say it depends on your operational experience, which protocol you're familiar with. OSPF v3 has done some rewrite, major changes, but it's still OSPF. You understand router network link states, you understand somebody external link state, you can start to understand OSPF v3 link state very quickly. But if you don't have the depth of OSPF understanding, then of course v3 is a learning curve for you. From ISIS perspective, there's not much to learn in case of ISIS if you've known ISIS and learned ISIS for a long time. So I know most SPs are pretty comfortable with ISIS, and there are large ISPs running OSPF too. So we all know full meshes problems exist for both protocol. Interesting challenges. Stability and scalability are more implementation based. Familiarity and comfort in both engineering and operations is very essential, and in my opinion, that's the biggest factor for selecting the protocol. What your engineering, not just engineering, what your operations staff is familiar with. So do we really need two protocols? This is the old debate, which is revived again recently because of IPv6. There's nearly complete overlap in functionality. Very, very similar. So depending, large ISPs have deployed ISIS, large enterprises have deployed OSPF. Some of the largest carriers in US have deployed OSPF. So there is a lot of experience out there. So finally, I love this quote from Dave Katz. He says, as long as there are two, people will never agree on one. So it entirely depends on your experience and your expertise. Thank you very much. Any questions? Any questions, any thoughts? Thank you, guys. Oh, by the way, my email address is SRAZA, Sam, Robert, Apple, Zebra, Apple. So if you're interested in a OSPF community presentation or ISIS legacy presentation, send me an email. I'll be happy to share it with you. SRAZA, S-Cisco.com. Sam, Rob, let me go. Yeah. SRAZA, Sam, Robert, Apple, Zebra, Apple, @Cisco.com.